In this lecture, I am going to discuss about torque acting on an electric dipole placed in an electric field. Okay, so in the last 2-3 lectures, I am discussing about an electric dipole. Electric dipole means two equal and opposite charges separated by a small distance. It is called electric dipole. Now, when you keep this electric dipole in an electric field, then there will be a torque acting on the dipole. In this discussion, I am going to explain about the torque acting on such an electric dipole when you keep it in an electric field. Okay, so before going on to the discussion about torque acting on electric dipole, all of you know that torque is the rotating force acting on an object. Okay, so in this case, electric field can be of two types. First one is uniform electric field, second one is non-uniform electric field. Uniform electric field means electric field intensity will have the same magnitude throughout the space. Every point, if you check, the electric field intensity will be same, then it is called a uniform electric field. Non-uniform electric field means the electric field intensity will be different, depends upon the point. At some point there will be maximum electric field intensity, and at some other points there will be minimum electric field intensity, and in between some other points there will be an average value of electric field intensity, like that. So electric field intensity varies, then such an electric field is called a non-uniform electric field. And when electric field is having the same value throughout the region, such an electric field is called a uniform electric field. So first we will discuss the case of uniform electric field. That means when you place an electric dipole in a uniform electric field, then how much torque will be acting on that. Okay, so let us consider the case when dipole is placed in a uniform electric field. So while representing uniform electric field, we will use straight lines for uniform electric field. If you want to represent a uniform electric field, what you will do is you will use straight lines to represent uniform electric field. Okay, straight continuous line represents uniform electric field. So I am considering a uniform electric field here. You can see that here all the lines are straight lines. Straight lines means it is uniform electric field. Okay, so that is how we will represent uniform electric field, by drawing straight lines. It means that it is uniform. And another thing is that we want to represent the direction of electric field. Electric field will have some particular direction. We want to represent the direction. Okay, so in order to represent the direction, we will use arrows. This is the direction I am giving. It means electric field is moving from left to right. Okay, here you can see arrow is pointing from left to right. So it means the direction of electric field is from left to right. And you already know that electric field is always directing from positive charge to negative charge. Here it is from left to right, which means the left side will have positive charge and the right side will have negative charge. That is why electric field is from left to right, because electric field is always pointing from positive to negative. Okay, now you need to place a dipole in this field. Okay, so I am placing a dipole in this field. Dipole means two equal and opposite charges. Okay, separated by some distance. So I am placing a dipole here in this field. This is my dipole. Okay, this is my dipole. This is minus q, this is plus q. This end is plus q and the other end is minus q. Okay, So this side, here is the dipole plus q and here is the minus q. They are separated by some distance. As you can see here, they are separated by some distance, and we already defined that the separation between dipole is always considered to be 2a. Okay, so from here to here there is a distance of 2a. Okay, now you can see that electric field is in the horizontal direction, but dipole is making some angle with the electric field. This is the electric field, and this dipole is making some angle with the electric field. Let us name this dipole. Let us name this side as A. This side of the dipole we can name it as A, and this side we can name it as B. Okay, now you can see that dipole is making some angle, so that the angle made by the dipole with the electric field is theta. Okay, so your dipole is making some angle which is theta. Okay, now from the diagram you can see that two charged particles are placed, one plus q and one minus q, which is called dipoles, plus q and minus q together. Okay, now when a charge is placed in an electric field, there will be a force acting on the charge, because you know that electric field is equal to force divided by charge. Then force is equal to charge multiplied by electric field. Okay, so there are two charges, and hence both the charges will experience some force. So let us find it. Force on plus q is equal to, what is the force on plus q, which is at A? Here you can see your plus q is here. What is the force acting on this plus q? You can see that this is plus q, this is positive charge. Okay, and this is negative charge. Your plus q is here. So the amount of force is given by this equation, that is q into E. Since it is plus q, this is plus q into E. Now what is the direction? You can see from the diagram itself, this is positive side. Positive will always repel this positive, and this negative will always attract this positive. So this negative will attract towards it, and this positive will repel this one. That means net force will be in, force acting on this plus q will be in this direction, isn't it? Because this will attract, that means this direction, and this will repel, that means again this direction. So the force acting on plus q is in right direction. Okay, so that you can towards right. Now in the similar way, there is one more charge, that is minus q. What is the force on minus q? That is equal to minus qe, because of equation 1. If you consider this as equation 1, then because of equation 1, force on plus q is qe and force on minus q is minus qe, when you keep the charges in an electric field, uniform electric field of electric field intensity E. Okay, now you can see that the force acting on this minus q charge is in which direction? From the figure you can find it. This is minus q, this is plus charge. Positive charge will always attract negative charge towards it, and negative charge will always repel the negative charge. So this will repel, means this direction, force will be in this direction, and this will attract, means force will be again in this direction. That means the direction of force is towards left. Okay, so the force acting on negative q will be towards left. Now you can see on the in the dipole, two charges are there, minus q and plus q. QE force acts on plus q and minus QE force acts on minus q. Both are acting in opposite direction. QE is on right direction, whereas minus QE is on left direction. Both are same in magnitude, QE, but they are acting in opposite direction. So what is the net force acting on the dipole? Net force acting on the dipole is QE. First one is QE, second one is again QE, but it is in the opposite direction. Okay, minus QE, which will be equal to 0. So net force acting on the dipole is 0 when you place it in a uniform electric field. You can see from here two forces are acting, one is QE, another is minus QE. So net force acting on the dipole means sum of two forces, QE plus minus QE, that is equal to 0. Okay, so there is no net force acting on the dipole when you place it in a uniform electric field, but there will be a torque acting on the dipole. Okay, net force is 0, but net torque is not 0. We need to calculate the torque. So consider the diagram. A force of QE acts on right direction and a negative QE acts on left direction. So net force acting on the dipole is 0, because plus QE plus minus QE, you will get 0. So net force acting on the dipole is equal to 0. Net force is equal to 0. We need to find torque, net torque. Net torque is not equal to 0. What is the reason? You can see here, one force is acting at this point, plus QE is acting at this point, minus QE is acting at this point. Equal and opposite, equal forces are acting, but they are acting at different points. Okay, when forces are acting at different points, torque will not be 0. Imagine that somebody is applying a force here, somebody is applying a force here. Net force will be 0, but there will be some torque, there will be some rotation. If you apply a force in the upward direction, if somebody is applying a force in the downward direction, both the forces are equal, then net force is 0. But still you can see that this will move, because you are applying an upward force, somebody else is applying a downward force. 5 Newton is applying downward, 5 Newton is applying upward, 5 Newton downward and 5 Newton upward. If you add, you will get net force is equal to 0. But still there will be a torque. You can see that this will rotate in the, this side will move up and this side will move down, isn't it? Even when net force is 0, so that you will get a net torque. So in this case also there will be a net torque, because the forces are acting at different points, line of action is different. So even though net force is 0, there will be a net torque. We want to find the net torque. So that in 11th you studied torque is equal to force into perpendicular distance. This is the equation for torque. Okay, here force you can consider anyone as QE or minus QE. We will consider only the magnitude. Okay, so both forces are QE. Force means we will consider only the magnitude of force, so that both are equal to QE. Okay, the negative sign in the force is nothing but the direction. Here first we will find the value of torque. Okay, so that you can consider that it is QE instead of minus QE and plus QE. In general you can consider that it is QE. Okay, now there is another quantity, that is perpendicular distance. Perpendicular distance, you can see force you will get QE, but perpendicular distance you don't know. But from the diagram you can find it. Perpendicular distance means from the first charge, line of action of first charge, to the line of action of second charge. What is the perpendicular distance? The distance is called perpendicular distance. Okay, so for finding that, consider this as the first charge, then extend this one till it meets this charge. So this will meet here. Now you got it. Then this distance if you find, that is AC. Okay, you can name it as, this one we already named A, name it A, this is B, and this one you can name it as C. Okay, so perpendicular distance, this is force into perpendicular distance is AC. Okay, so previously itself we defined that it is making an angle theta with the electric field. Now from that triangle, ABC, okay, what is sin theta? Sin theta is equal to opposite side by hypotenuse. What is opposite side here? It is AC by AB, or AC is equal to AB into sin theta. Now what is AB? AB is 2A, dipole length, 2A into sin theta. So you got AC, perpendicular distance you got. Okay, perpendicular distance is AC. You got AC as 2A sin theta. Now what is torque? Torque symbol is tau. It is a vector that we will come, is equal to force. What is the force? QE into what is AC? 2A sin theta. Now this is equal to, you can write it as, you can take E out, then Q into 2A sin theta. Okay, I am just rearranging. Now what is Q into 2A? This quantity you already know, Q into 2A. Q into 2A is P, dipole moment. So this quantity is P into E into sin theta. Okay, so that the expression for torque is P into E into sin theta. Now PE sin theta means, you know about cross product, P cross E. This is the torque. Okay, because A cross B is equal to AB sin theta, so PE sin theta is equal to P cross E. Okay, so torque acting on this dipole is P cross E. It is not equal to 0. Okay, now we got torque acting on the dipole is equal to P cross E. Now let us discuss some cases. This is equal to PE sin theta when theta is equal to 0 degree. What is theta here? Here you are having an electric field, and in that electric field you are placing a dipole. Okay, so in that electric field you are placing a dipole. Now what is the theta here? Theta is nothing but the angle made by the dipole with the electric field. This is the electric field direction. This side is plus, this side is minus. So theta is the angle made by the dipole. Now when you place it like that, what happens? When theta is equal to 0, what is torque? PE sine 0, that is 0 because sine 0 is 0. When theta is equal to 180 degree, again torque will be 0. So torque will be 0 when theta is equal to 0 or 180 etc. That means when you will get theta is equal to 0, when your dipole is along the direction of electric field. That means when dipole is parallel to electric field. From the diagram you can see, when your dipole is in the same direction as that of the electric field, theta will be 0. There won't be any angle. Then torque will be 0. That means when you keep your dipole in the same direction as that of electric field, your dipole will not rotate. It will be in the same position. Okay. Now let us consider another case. Case 2. When theta is equal to 90 degree, torque is equal to PE sine 90 means 1, that is PE. This will be the maximum torque. Maximum torque you will get in this case. What does it mean? This is your dipole. If you place your dipole perpendicular to your field, okay, in the initial case what you are doing is you will have an electric field like this, and you are placing your dipole also like this. This is the first case which we discussed. Okay, when theta is equal to 0 degree, this is the case. Theta is equal to 0. That means your dipole, this side will be minus q and this side will be plus q. When you place your dipole like this, the dipole will be in the same orientation throughout. It will not have any torque because torque is equal to 0. Your dipole will be in the same position. This is when theta is equal to 0 degree or 180 degree. Now when you place your dipole, if this is your electric field, and when you place your dipole like this perpendicular to the field, okay, this side let us represent this side as my plus q and this side as minus q. Here in this case you can see that angle theta is equal to 90 degree because you can see theta is nothing but this angle, that is 90 degree. In the first case theta is 0 or 180 degree. 180 means minus q will move to right direction and plus q will move to left direction, then it is 180. Okay. In the second case theta is equal to 90 degree. When theta is equal to 90 degree, torque is maximum, that is PE. So that what it means is, when you keep your dipole like this, dipole will not stay there. Immediately it will rotate. Okay, this is the initial orientation. If you keep like that, dipole will not stay like this, but it will rotate because there will be maximum torque acting when you keep it like this. Maximum torque means maximum rotation will be there, so that immediately this dipole will rotate. When you take out your hand, this dipole will rotate. Okay, it will not stay like this, it will rotate. Maximum rotation will be there. Here there won't be any rotation if you keep it like this. And in between this configuration and this configuration, any other configuration will also rotate, but not this much of rotational force will be there. This is the maximum rotational force and this is the minimum rotational force case. In between that there will be rotation, not up to this one, but there will be rotation when theta is not 0 or 90. Okay, so other than 0 or 180 degree or 360 like that, rest of the angles, here in this case we will not define 360 etc. because 360 means 2 times you are rearranging the same dipole, means it will be again 0. Okay, so we need to discuss only up to 180 degree. So other than 0 or 180 degree, all the other angles your dipole will rotate, and the maximum rotational force, that is torque, will be when you place your dipole perpendicular to the field. Okay, so this is the case for torque acting on a dipole when you keep it in a uniform electric field. Okay, now instead of uniform electric field, if you keep it in a non-uniform electric field, then what happens? Let us see. Non-uniform means you can't draw straight lines. Non-uniform field means field will be like this. Okay, this is non-uniform electric field. Now if you keep your dipole in this field, then what happens is your dipole is like this, making some angle. Then what happens is the force acting on the dipole will not be zero. Net force acting on the dipole will not be zero, because this end will have a force Q into E. If this is plus Q, this side will have a force minus QE if this side is minus Q. But non-uniform means E is not same everywhere. Non-uniform means electric field is not the same everywhere, so that the electric field value which is here may not be equal to the electric field value which is here. At this point some electric field will be there, at this point some electric field will be there, at this point some electric field will be there. All the electric fields will be different. Such a field is called a non-uniform electric field. So this E is different from this E. That means this QE is different from this QE. They are not equal. When they are not equal, net force equal to QE, you can call it as E1 because they are different. This is E2, QE1 plus minus QE2, that is Q into E1 minus QE2. You can see that it is not equal. So when you keep a dipole in a non-uniform field, and dipole is in non-uniform field, there will be net force as well as net torque. Okay, and when you keep the same, when kept in uniform field, there will be net torque, but net force is 0. So these are the two cases, when placed in uniform field and when placed in non-uniform field. So I hope it is clear.